地球大部分是什么颜色。现在这个地方是云，这边也是云，现在白白的是云。
为什么看不到月球的背面？
Vision is one of the principal methods we've used to explore our surroundings since birth. Since ancient times, people have aspired to look at the world from a higher position, from further away, from different angles and perspectives. Yangming Wang, the Ming Dynasty philosopher, dreamt of looking at the Earth from space with eyes as big as the sky. However, nowadays, few have had the chance to actually fly into space and view the Earth's surface, other than a handful of astronauts, till it came along. "1,600 times taller than the Taipei 101. "80 times faster than a Ferrari. It can survey vast dimensions and acquire extensive measurements in an instant. Its sensors possess powerful capabilities to see what the human eye cannot. Day and night, it takes not a moment's rest, guarding our world 24/7. It is the remote sensing satellite. Remote sensing refers to observing and sensing an object from a distance without making physical contact. Just as we view the scenes before our eyes, the eyes of the satellite are high-precision sensors which observe surfaces from remote distances. And that's why it's called a remote sensing satellite. A huge parabolic antenna revolves as the satellite orbits its tracks. Located in the Center for Space and Remote Sensing Research, National Central University, it is the first resource satellite receiving station in Taiwan, capable of receiving satellite signals within a 3,000-kilometer radius. With the station's satellite data processing system, precise geometric processing and corrections are performed to obtain high-resolution satellite imagery. This is an image acquired by a satellite from an altitude of several hundred kilometers. The multispectral sensor in satellites is a high-tech product. In addition to visible light, it also detects near-infrared, thermal infrared, microwave, and radio wave. These electromagnetic radiations are invisible to the human eye. Therefore, it can see much more than our eyes are capable of. For example, from the bleachers of a ballpark, it is difficult to distinguish between a natural and an artificial grass field with the naked eye. This is because natural grass and artificial grass have similar energies within the visible spectrum. They all look green. There does not seem to be much difference. But at near-infrared frequencies, natural grass delivers an energy much greater than artificial grass. This is how the satellite's multispectral sensors are able to distinguish between them. After receiving data from the satellite, we may obtain a large amount of geographical information, including relevant point, line and plane positions in space and their distributions. After this data is digitized and integrated through a powerful software and hardware system, various analysis and interpretations may be performed. We call this system the Geographic Information System, GIS. Researchers are analyzing a set of newly obtained satellite images. According to comparisons made by GIS, a luminous spot has appeared in this position, which did not exist before. By zooming in the high-resolution satellite image, it can be seen that this change is not a natural phenomenon, but man-made. Based on the information we have, this should be the metal roof of an illegal factory. Researchers record the spatial coordinates and deliver them along with geographic information to relevant managerial units, then await verification from actual field surveys. If the satellite is the human's third eye, then this system is a brain with super high processing capacity. From a small illegal building to a large-scale overcropping and digging, and even a ship dumping oily waste in the middle of the open sea, a satellite sees it all as it orbits around the Earth. Sunlight is the main source of electromagnetic waves from objects detected by remote sensing satellites. When sensors passively receive solar energy reflected from the surface of an object, it is called passive remote sensing. At night, or in bad weather conditions, when sensors on satellites voluntarily emit energy, such as radar, it is called active remote sensing. Radar has excellent penetration capability, allowing it to easily penetrate obstructions like clouds, smoke, or dust to reach ground surfaces and be reflected, and then detected by satellites. In this way, large-scale terrain data can be provided throughout the day. In the past, measurements of land surface deformation had to be made by people on site. This meant excessive travel, and measurements were often inaccurate. When faced with mountains, oceans, and other topographical barriers, large-scale measurement became impossible. Satellite radars measure by scanning with radio waves. The phase and amplitude data brought back by radar echoes have superior coverage and precision. A satellite in orbit has a predetermined course and observation cadence. It passes over the same target area every once in a while. As such, it is able to repeatedly compare observations within a short period of time. At 1:47 a.m., September 21st, 1999, a violent shake woke a quiet town in Nantou, Taiwan. This earthquake, with Richter magnitude of 7.3, triggered a large-scale faulting, which caused many surface ruptures in Taiwan. Houses collapsed, and inestimable loss of life and property damage resulted. It is known as the 921 earthquake. Cholumpu Fault is where the largest displacements were found after the 921 earthquake. Land surface deformation is evident from the uplifted mounds. In the Center for Space and Remote Sensing Research, Researchers are interpreting satellite radar images taken before and after the 9/21 earthquake. Deformations in the land surface lead to changes in the distance between the surface and the satellite and cause differences in radar phase. Researchers often paint phase changes in different images with colors of the rainbow to generate an interferogram. Circular fringes in the interferogram reflect the extent and scope of surface deformation. This technique is called the interferometric synthetic aperture radar, INSAR. By comparing our interferograms before and after the 9/21 earthquake, we noticed that a large number of fringes appeared around the Cholongpu Fault, which are marked by a black line. Each circle represents a deformation of 2.8 centimeters. From this, we can calculate that the center of fringes, or the location with maximum deformation, has a subsidence of about 30 centimeters. Frequent natural disasters have taught those who live on this land to respect and appreciate the heavens. Curling upwards, the incense smoke carries the pious prayers of the believers drifting up. Are there really gods watching all this from the heavens? We do not know. But there really are thousand-mile eyes in space, continuously watching the world. Satellites orbiting the Earth not only enable us to observe the surface, but also to fully grasp all kinds of atmospheric phenomena. Changes in weather affect our everyday lives. People nowadays are used to arranging their schedule based on weather forecasts. Forecasts mainly contain analysis of the current atmospheric state. In the past, collection of atmospheric data mainly relied on ground stations, but there are many areas on Earth, such as oceans and polar regions, where ground stations are rare. Satellite data covers these gaps precisely. Satellites are able to observe atmospheric phenomena thousands of kilometers away. Many meteorological changes can be seen on the cloud atlas as they develop. Ground stations would not have been able to make observations at this early stage. Besides utilizing the satellite cloud atlas to analyze various weather systems and monitor rapidly developing storms, precise sensors on the satellite may also obtain information that was previously impossible to obtain with traditional instruments, such as using microwave and infrared images to analyze cloud type and height and calculate the temperature of ground and water surfaces. Satellites which carry rainfall radars provide better rainfall monitoring to help us make more accurate weather predictions. From astronomy to geography, the comprehensive coverage of satellites provides abundant and powerful information. When seeing is not just seeing, have we not in our hand a key that opens up more and more possibilities? GPS used in car navigation, the Global Positioning System, is a good example of how satellite technology may be applied to everyday life. Many of us have had this experience. While driving on an overpass, the car navigation system thinks it's on a ground-level road, causing misdirection. This is because electronic maps in car navigation systems are planar, unlike the real world, which is 3D. If we could create a virtual reality by applying 3D effects to all the buildings, bridges, and roads in the electronic maps, the problem could be effectively solved. Researchers in the Center for Space and Remote Sensing Research use a mouse to navigate freely between buildings and streets on screen. This is a so-called digital city. Just like 3D virtual worlds in modern movies and games, the realism of the experience keeps our eyes glued. But unlike movies and games, this world is not just imagined, but consistent with the real world. To build a digital city, first, satellite images or navigational maps are needed as a base on which 3D housing models are built, in coordination with terrain contours. Next, apply wall textures one by one, correct image geometry, and integrate these properties. All figures used in the digital city conform to reality as much as possible. Therefore, this 3D virtual reality created matches the real thing in shape and size. This is a building which will undergo urban renewal. Although reconstruction has yet to commence, through the architectural plans, we can already see what the result will look like in this digital city. Through this, we can determine whether or not this new building will match the existing landscape. Exterior colors can be applied freely to help our judgment. Even sunlight on the building can be simulated to see the extent of shadows and their impact on the surroundings. Everything is true to life, and thus all the more convincing. The satellite quietly gazes at this beautiful planet. Overlooking this world from hundreds of kilometers away, horizons widen, voices disappear. The tranquil land appears harmonious and beautiful. Perhaps it is impossible to see the complete picture of everything, but by observing and thinking from different viewpoints, different angles, you will see a different world.